All right, welcome everybody. Good morning, good afternoon, good evening, wherever you are. My name is Jack Dekkers, Iowa State University, and I'm one of the co-PIs on the Agricultural Genomes to Phenomes Initiative, funded by USDA NIFA. Which we're very grateful for the funding they provide for this activity, but also for other activities that we're doing in AG2PI. Especially the seed grants. So the field days are really designed to expose the community to relevant research that's going on, especially focusing on things that impact both the livestock and the crop side of genomes to phenomes. So today we're going to approach it more from the animal side, but hopefully we can also identify needs for forages in particular. So we're going to talk about mitigating methane emissions in dairy cattle through genetics and nutrition, with the need and implications for the need to improve forages. So we have two speakers. The first presenter is Dr. Francisco Peñagaricano. He's originally from Brazil. He's an assistant professor in the Department of Animal Science at the University of Wisconsin. And he's going to talk to us about omics tools to mitigate enteric methane emissions from dairy cattle. And then that will be followed by a presentation by Ermias Kibriap, and I'll introduce him more extensively when we get to his talk. But I'm going to turn it over to Francisco first. As usual, if you have questions, just put them in the chat. And if the question is immediately relevant to what the speaker is talking about, then I'll interrupt the speaker and we'll address the question right there. But then we'll also have opportunities to general discussion after the talks. So with that, Francisco, I'll turn it over to you.
Perfect. Let's see. Can you guys see my presentation?
Yes, we can.
Excellent. Thank you, Jack, for the introduction. It's great to be here, and thank you all for joining this webinar this morning. I have a bunch of friends in the chat here, and I'm originally from Uruguay, no Brazil. So guys, stop making shows. Listen, we will be talking about mitigating methane emissions this morning because we care about sustainability. And here I have one definition of sustainability, one that I really like. Sustainability as meeting the needs of the present generation without compromising the ability of future generations to meet their own needs. And as you can see here, I have the three dimensions of sustainability: the social, the environment, and the economic. And I have highlight some of the challenges that we have of sustainable farming, including climate impact, climate change, water and soil quality, animal welfare, profit, and productivity. Now, if we think about sustainable dairy farming, we will think about a sustainable dairy cow, a happy cow like this one, right? A cow that somehow is socially responsible. So we will be thinking about a high production cow, because if we produce more milk with the same amount of cows, that will have a positive impact on the sustainability. Or even if you want to think, if we can produce the same amount of milk with the less number of cows, that will have a very positive impact on sustainability. Of course, we are talking about a very fertile cow. We know that fertility, reproductive performance, has a very positive impact on dairy farm profitability. And of course, we are thinking about a very healthy, long-lived cow, so we don't have problems with animal welfare, animal well-being, and the use of pharmacological interventions. And of course, we would like to have a very efficient cow. We would like to produce the same amount of milk, but using less feed. That will have a very positive impact on the system, and why not have a cow that produce the same amount of milk but with low methane emissions. And for those that are geneticists here, you know that genetic selection is in fact a critical tool to achieve these sustainable goals. So how important is genetic selection? I'm showing here the change in milk production per cow per lactation in the last 60 years here in the United States. And as you can see here, clearly there has been a tremendous increase in milk production per cow per lactation. In fact, a dairy cow today, she produces more than twice as much milk as a cow 60 years ago, and more than half of that improvement is due to genetic selection. In fact, genetic selection is a very powerful tool for achieving lasting gains in dairy cattle performance, and contrary to improvements in nutrition, in management, in cow comfort, the changes achieved through genetic selection are incremental, cumulative, and permanent, what makes genetic selection a very cost-effective strategy. So this table shows the traits that we have under selection. So we are selecting for more production, we are selecting for more fertility, we are selecting for longevity, for more health, even calving ability, some functional feed traits, and even today for feed efficiency. In fact, feed efficiency is the most recent trait introduced in the national evaluation. And as you can imagine, selecting for feed efficiency has a tremendous positive impact on this idea of sustainable dairy farming. So what's the importance of feed efficiency? Well, feed represents more than 50% of the total production cost in a farm. And there are multiple benefits of improving feed efficiency, including increasing farm profitability. Basically, we can produce the same amount of milk, but using less input, less feed. And of course, we will reduce the environmental impact of dairy farming, because if we can produce the same amount of milk with less feed, we probably will need less land, we will generate less manure, and probably we will emit less greenhouse gases. So how do we measure feed efficiency? Well, in dairy cattle and also in beef cattle, we measure feed efficiency as residual feed intake, the difference between observed and predicted intake. Imagine we have a group of cows and we are able to measure individual feed intake, and somehow we can predict the intake of that cow based on body weight, based on change in body weight and production. And then you will see we have cows like this one, that she's eating roughly 15 kilos of dry matter intake per day, but based on her body weight and production, she should be eating roughly 20 kilos. So it's a cow that she's eating less than what we predict. It's a cow that has a negative residual feed intake. That means it's a very efficient cow. And then we will have cows like this one here. This is a cow that is eating roughly 24, 25 kilos of dry matter intake per day, but based on her production and body weight, she should be eating roughly 18 kilos. So she's eating much more than what we predict. She has a very positive residual feed intake, and it's a very poor efficient cow or less efficient cow. So this effort, the dairy cow feed efficiency effort, started 12, 13 years ago, including 4 land-grant universities, the USDA, and federal funds, and also industry funds. And nowadays, we have feed efficiency records in more than 8,000 lactating Holstein cows. So we measure feed intake daily and milk production daily, and we measure milk composition 4 times a week, and we measure body weight once or every 2 weeks. And we also collect other records. We are collecting spectra, body temperature, we have activity and rumination, and we have also some metabolites. So we measure feed intake in our research farms, And we measure feed intake, individual feed intake using these automatic gates that you see here in my left, or Cullen gates as we have here in the middle, or even we measure feed intake in tie stalls, as you can see here in the right. And at the end, we calculate residual feed intake as the difference between what we observe and what we predict. And in order to predict, we use these three classical energy sinks: milk energy, that is based on milk production and composition; metabolic body weight; and change in body weight, that is based on body weights. And basically, we obtain residual feed intake using this model that considers the three energy sinks, some fixed effect as days in milk and lactation, and also some random effects, in this case, for example, cohort. And then we decided to express this feed efficiency trait as feed safe. Feed safe actually combines residual feed intake and body weight composite. Feed safe was implemented in December 2020, so it has 2 years. And it represents the expected pounds of feed safe per lactation, and then larger positive values are more favorable. And as you can see here, we have a beautiful distribution for feed safe PTA values in the Holstein population. We have more than 450 pounds of feed safe between the extreme, between what we call high efficient cows and those that are less efficient cows. So we are breeding for a more socially responsible cow, high production, more fertile, more healthy, long-lived. She is feed efficient. What about low methane emissions? Well, let me go some numbers first here. So methane, you know, represent 11% of the total US greenhouse emissions in the United States, and is the second most important greenhouse gas after CO2. And enteric fermentation accounts for 27% of total US methane emissions, and is the second most important source of methane emissions after natural gas and petroleum systems. Now, from an energy perspective, enteric methane emissions represent a loss of energy. It's an energy sink. Between 6 and 12% of gross energy intake, that's energy that could be otherwise be available for growth of production. So reducing enteric methane emissions would have multiple benefits. Not only a positive impact on environment, but also improving production efficiency and probably farm profitability. So that's why a group of institutions, including 4 land-grant universities here and the USDA, we proposed this proposal entitled Integrating Genomic, Milk Spectrometry and Microbiome Manipulations to Mitigate Enteric Methane Emission from Dairy Cattle. And our overall goal is to reduce enteric methane emission from dairy cattle by combining 3 different aspects: selective breeding, the use of milk spectra data, and some rumen microbiome interventions. This proposal was submitted to the Greener Cattle Initiative and is still under review. So what's our plan? What are we proposing? Well, we are proposing phenotype a large group of cows, at least 4,000 in a short period of time, and we will do that in our research farms. Why in our research farms? Because in our research farms, we can measure individual methane emissions and individual feed intake daily. And of course, we will measure milk production and milk composition, so we can calculate milk energy. We will have body weight, and we will have milk spectra, and we will do that for at least 6-8 weeks in mid lactation. And we are planning to address 3 different components. One is selective breeding, and actually we will do that in order to develop national evaluation for methane emission traits. We will evaluate the use of milk spectra to predict methane emissions, and we will also target the rumen. First, we will reveal the composition and activity of the rumen using extreme animals, extreme cows, in terms of low and high methane emissions. And we are also planning to do a quite cool experiment where we will exchange the ruminal contents between low and high in order to separate, decipher the relative contributions of host and microbes. So what about phenotyping? Well, there are different methods for phenotyping methane emissions. We have here in my left respiration chamber, and of course it's the gold standard. Now respiration chambers are extremely expensive and labor intensive, and therefore limited to a few animals. We can use SF6 tracer techniques that is somehow somewhat more scalable than a respiration chamber, but requires rumen boluses, daily animal handling, and lab measurement of gases. And then we have two different methods that are becoming quite popular, especially when we think about population studies like the green feed system or the use of snippers, typically in automatic milking systems, but you can have also snippers in feeders. And there are also some laser detectors. So I will go briefly over each of these methods, showing the advantages and the disadvantages. So respiration chambers, again, those are the gold standard method that we have for measuring methane emissions, are extremely expensive and very labor intensive, and hence the throughput, or basically the number of animals that we can phenotype, is very low. But of course, we have to recognize that it's an extremely precise and accurate method. And because we are talking about a box, basically it's in confinement, so there is a high alteration of the cow behavior. We have the SF6 technique. It's popular in grazing systems. It's cheaper than the respiration chambers, but it's very labor intensive. It requires daily animal handling and the measurement of gases in the lab, and the throughput somehow is limited. I put here from low, medium, but it's a very, very precise and accurate method. Then we have the green feed system. The green feed system is cheaper than respiration chambers and also SF technique. The throughput it's at least a medium, and it's a quite precise, accurate method with almost no alteration of the cow behavior. And of course, we have the sniffers. The sniffers are even cheaper than the green feed, and because you can install the sniffers in milking robots or in the feeders, actually you can phenotype a large number of animals. That's why for throughput I put here high, and probably it's precise enough, but less accurate probably than the green feed system, and there is no alteration at all of the behavior of the cow. And at the end is the laser detector. I mean, it's probably the cheapest method that we have in this table. It requires a lot of people. It's quite labor intensive, and probably it's a method with the lowest precision or accuracy that we have. So here in US, we are using the green feed system in our research farms to phenotype methane emissions. Research has shown that this system delivers reliable estimates of enteric methane emissions. And the key to actually obtain reliable estimate is to obtain a large number of short-term records measured at different times of the day during multiple days. And because our cows are exposed to the green feeds 24/7 during 6 to 7, 6 to 8 weeks, we actually obtain several short-term records during the day for multiple days, what is very good. The other thing is when you use green feed, you obtain directly production as grams per day, and that has a positive impact when we define traits. So what about selective breeding? Well, selection is a promising tool to mitigate enteric methane emissions. Recent studies have shown that the methane emission traits are heritable. However, until now, no country has developed a genetic evaluation for methane emissions, basically because methane emissions is a difficult trait and expensive trait to measure. Now, in the genomics era, genomics has facilitated the selection for traits like methane emissions or even feed efficiency because we can phenotype a relatively small number of cows, and then we will use this population, known as reference population, to predict genomic breeding values for the entire population. So our goal here, our dream is first develop a reference population for methane emissions, then develop genomic evaluation for different methane emission traits, and finally, quite important, facilitate the incorporation of this methane emission trait into selection indices. So what's about trait definition? Well, we have at least 4 alternative ways to define methane emissions. We can calculate methane production as grams of methane per day. And we are using green feeds, and when you phenotype using a green feed, you get directly actually grams of methane per day. We can calculate or define methane emission as methane yield, and that is grams of methane per kilogram of dry matter intake. And because we are measuring methane emissions in the same animals that we are measuring feed intake, we are able to calculate actually methane yield as the ratio of methane production divided by kilogram of dry matter intake. We can also define methane emission as methane intensity. That will be grams of methane per kilogram of energy corrected milk. And of course, because in the same animals that we are measuring methane emissions, we are measuring milk production daily and milk components, so we are able to calculate energy corrected milk. Now, as you see, both methane yield and methane intensity are ratios, and ratios are probably not the best traits to work with, at least in national evaluations. So probably the fourth definition, it's better, and it's called residual methane production. Is like the residual feed efficiency, where we calculate the grams of methane regress on different predictors. And here I'm including at least 3 of them: dry matter intake, body weight, and milk energy. So I'm showing here the heritability estimate for different methane traits. This is a meta-analysis that was published a few weeks ago. You have here methane production, methane yield, and methane intensity. And as you can see here in this column, the heritability estimate for these traits range between 0.18 and 0.24. Just to have a reference, the heritability for production trait is around 0.20. So this means that methane emission traits are as heritable as, or even more heritable than production traits. And those are great news, because that will allow us to actually move fast through genetic selection. I'm showing also genetic correlations here, and I'm showing the genetic correlation between methane production and 3 production traits: milk yield, fat yield, and protein yield. And we have here the genetic correlations and the 95% confidence interval. So you can see that methane production is positively correlated with both milk yield and fat yield. this positive correlation is actually unfavorable because we want to reduce methane emissions, but we don't want to decrease production traits. So I mentioned that we will also target the use of milk spectra. Infrared spectroscopy is actually a very powerful phenotyping tool. Think about it as high throughput, low cost, non-invasive, and if we use milk spectra, we can actually obtain real-time predictions. And milk spectra has been used to predict different complex traits in dairy cattle with different degree of success. And these complex traits include energy status, metabolic profile, health status, fertility and pregnancy status, among others. So our goal here is actually determine the value of using milk spectra to predict methane emissions. And for that, we will have a quite large population with spectra data and accurate methane emission estimates. I'm showing the result of a recent paper published by the group in Guelph, Canada, where they predict methane emissions using spectra data and different artificial neural networks. I know this table has many numbers, just please focus on the R. R is the predicted correlation. It's basically the Pearson correlation between observed and predicted methane emissions. This paper it's very cool. They use different predictors. And if you use milk yield or fat yield or protein yield in order to predict methane emissions, you get predicted correlations 0.3, 0.4. Now, as you can see here, when you use spectra data, you get predicted correlation up to 0.7. So these results are very promising. If we can use milk spectra to predict methane emissions, then we will have real-time predictions nationwide in terms of methane emissions, and we can use that for management and also improve the accuracy of the genomic breeding values. And the third component is the rumen microbiome. As you know, enteric methane is formed exclusively by methanogens in the rumen. So of course we have to target the rumen. Now, this is a very interesting system, but it's complicated. And I like to think about this system using this diagram here, graphical model, where you can have actually the rumen microbiome in terms of composition and activity that affect methane production, but we will have also the host or the cow genome that can influence the rumen microbiome. So you can think when you are in front of this system that we will have a direct effect of the cow or methane production. We will have an indirect effect mediated by the rumen microbiome. You will have a total effect. So basically, you can model this direct, indirect effect using structural equation models and graphical models. And our goal here is basically first reveal the rumen microbiome in terms of composition and activity affects methane production. And for that, we will target cows with extreme methane emissions. And at the same time, we will assess the relative contribution of host and microbes to methane production using analytical tools as what I just described, but also we will exchange the rumen content of extreme animals to see or to learn about these different contributions. I'm running out of time, so I will show you some of our potential solutions of outcomes. So we will have our genomic solutions. Basically, we plan to have genomic evaluation for methane emission traits in US dairy cattle. And remember that the changes achieved through genetic selection are incremental, cumulative, and permanent. I show you using data from milk production, so it's a very cost-effective strategy. We will try to provide also spectra-based solutions. If milk spectra is a good predictor of methane emissions, think about it, we can use spectra to increase actually the accuracy of genomic evaluations of methane traits, but also, very importantly, we will have real-time nationwide predictions, so we can use that data to optimize cow management in the dairy farm. For example, if we identify those high-emitting cows, we can assign those cows to specific diets. That's probably are more expensive. And we will try to have also microbial solutions. First, a deeper understanding of how the host influence the diversity and activity of methanogens, and then develop strategies to reduce methane formation in the rumen. With that, let me finish with some take-home messages. I'm sure you are aware there is a growing public and consumer scrutiny over dairy farming, and some of the concerns are related with animal welfare, the use of pharmacological interventions, and the environmental impact of dairy farming. And in this context, there is no discussion that genetic selection is a critical tool to improve dairy sustainability. We have in place now very robust programs for improving production, health, fertility, and even feed efficiency. So our current challenge is actually target methane emissions. We want to decrease enteric methane emissions. For doing that, we have some knowledge gaps. First, the lack of genetic tools to select directly against the methane emissions, and an incomplete characterization of the rumen microbiome, particularly the methanogens. Now, the benefits in this field are multiple, including selective breeding as a tool, management interventions based on the predictive power of a spectra to detect or to predict methane emissions, and microbial manipulations. With that, again, thank you, Chuck and the team, for the invitation. And of course, I'm open for questions.
Okay, thank you very much, Francisco. Very interesting work and very important. There's a number of questions in the chat already. Please add more. We're not going to be able to get through all of them, but Francisco can also answer some of the questions online. Let's see. The one question about genetic correlation between methane emissions and feed efficiency. Have you looked at that?
Well, we haven't yet, this meta-analysis that I showed, it didn't have those. There are probably few data sets that are able to answer that question. The other thing is, it will be interesting to see how you define actually methane emission, right? If you define methane emission as methane production, probably a very efficient cow will be able to extract more or digest better the same amount of feed and produce maybe more methane from that. If you use residual methane production and you use residual feed intake as a predictor, then you are probably creating these two traits as independent that could have an advantage in terms of genetic evaluations if you have independent traits.
Yeah, but you mentioned that methane is an energy sink, right? So you would expect that if you select for feed saved, you would also reduce methane production per kilogram of dry matter intake, or
probably per kilogram of milk.
Because
you are producing the same amount of milk, you consume less feed, you will produce less methane. So we will expect a positive and favorable genetic correlation between methane intensity and residual feed intake. probably we will expect a negative correlation between methane yield and methane and residual feed intake. So again, I think it depends on how you define the trait. It's interesting, but you have to be careful.
Yeah. So another question, and we'll hear from the next speaker about the impact of diet on methane. But the question here is that methane measurements must be feed diet related. What kind of feed is used in the experiment, and in practice, what are the main components of different feed used by dairy farmers in the US?
Yeah, no, that's a great question, and Ermias is our rock star. He will be presenting after me. What I will say is, in our case, the way that we measure methane emission, we have a group of cows, a cohort of cows that are receiving, by definition, the same diet. So then we are able to actually block by diet, and then we sort inside that as high efficient, less efficient. So what I'm trying to say is this phenotyping is somehow independent of the diet that we are feeding, because we consider the cohort, the group of cows that receive the same diet at the same time in the same place in the model.
Mm-hmm. But across the different research stations, will the diet be standardized?
No, the diets are not standardized. I will argue that are probably similar diets, mostly the research farms that are here in the Midwest. Mm-hmm. But the cohort somehow also adjust by differences between research farms, right?
Yeah.
But a question related with that is interesting is there a genetic, is there an interaction between the cow genome and the diet, right? And that is probably something that we will need to target in the future. If you have the same group of cows and you provide two extreme diets, high and low in forage, for example, is there a re-ranking of the animals? If that's happened, that will be a problem, right? Because we will need to adjust or consider diet when we present the genomic evaluations.
Mm-hmm. Yeah, yeah. And then you have pasture-based production too. I mean,
yes.
Or
yes.
then it's maybe more difficult to measure, but that could introduce quite a bit of G/E. So another question is there a plan on how to incorporate microbiome information in routine evaluations?
Well, that's a great question. There has been research in pigs and also in dairy on how to model the rumen microbiome, and we can model the rumen microbiome in a similar way that we actually model the SNPs, right? And then you have a relationship matrix among animals based on how similar is the rumen microbiome. That could be something to explore if you can actually improve the prediction of breeding values. I think the research on the rumen microbiome is, what if we find some key microbes that we can actually manipulate or basically provide to the animal, either at the beginning of the lactation or when it's a calf, and you are actually intervening the rumen of that animal, and that animal will end up producing less methane somehow. And I know Ermias is working on this, and he's planning to show some of these potential manipulations in the rumen in his presentation. So there are multiple ways, right? It could be at the level of, can we get better predictions, or can we learn about the rumen to then actually learn how to manipulate the rumen in a short term for a lactation, or for the entire life if we actually manipulate the early life.
Mm-hmm. Okay, question here. What are the economic incentives to incorporate methane emissions into?
Oh, that's fantastic. That's a very good question, and that's a really important one, right? Because if we have methane emissions traits, we want to incorporate those in the selection index. But in order to include those traits in the selection index, we need an economic value for that trait. And that is actually the $1 million question. What will be the economic value? And we are not the only ones. Different groups around the world are working to try to find what will be the economic value. Right now in this country, we do not have an economic incentive. Maybe in the future we have, you know, how we can have, for example, organic milk. We can have a milk that actually is associated with less methane emissions, and that brand will pay more, and there you have a incentive. We don't know.
Yeah. Christine Baas from Guelph just put a comment in the chat on this. She quotes a price of $50 per ton per ton of CO2. So if that's implemented, and you know, that would be even higher for methane, of course, then potentially, as she indicates, the economic value could be huge.
Right. I say we don't have national evaluations today, but Canada will be, I think, the first one implementing a genomic evaluation for methane emissions in April. It's coming soon. And my understanding is based on spectra data, and basically the paper that I show in my presentation.
Yeah. There are more questions, but we're gonna close this off right now and move on to the next speaker. But
thank you very much, Jack, again for the invitation, and thank you all for joining my webinar this morning.
Yeah, and apologies for having you originate from Brazil. That's like saying that somebody who's from the Netherlands is from Germany. Oh, I know you.
No,
I
think the Brazilians weren't happy. That's why I had to. Yeah.
So we may come back to some of the questions after the next speaker, but if not, then we are going to send all the questions to the speakers, and they then have the opportunity to respond to you later on. And this is all being recorded, so you can also look back at the recording later on. So our next speaker is Ermias Kibriap. He is an associate dean and Cessnon endowed chair in sustainable agriculture at the University of California, Davis. And he is going to talk to us about the diet side and implications for forages, mitigation of enteric methane emissions through nutritional intervention. So Ermias, please go ahead.
Thank you very much, Jack. I hope everybody can hear me and you can see the slides as well.
Yes, we can.
All right, great. So following that great presentation by Francisco, now we're going to be talking a little bit more on the nutritional side of things, but I will refer back to what Francisco has shown as well, because there is a link between the nutrition and the genetics aspects of trying to reduce enteric methane emissions. So just to start us off, I'll be just giving you an overview of why methane is important, and what is the contribution of agriculture in greenhouse gas emissions. So here you can see that the lion's share, about 3/4 of the environmental impact comes from the energy sector, and the agriculture and forestry and land use is about 20% or so. And some of that is from livestock, including enteric and manure, and then you have agricultural soils, rice, and so on and so forth. Coming down into the livestock emissions, how it is divided. Again, Francisco has alluded to this. What is the importance of methane within the U.S. framework and also globally? There's a big contribution, about 35% of methane coming from livestock, and it depends what species we're looking at, right? From beef cattle, it's mostly from the enteric emissions in the front end. Dairy, again, depending on how the manure is managed. If it is managed in a lagoon kind of situation, then you have emissions coming from that, quite substantial emissions coming from that, but still the enteric emissions are also the majority is enteric emissions, and from swine it's mostly from manure. And I'm sure you've heard a lot of talk about agriculture trying to get to net zero. There's been a lot of targets, regional targets, state targets in the US, or country targets and global targets. And if you look at what are the solutions, this is from McKinsey and Company, who analyzed what are the opportunities in agriculture to get to this net zero. A lot of it's in this light blue kind of thing. I'm colorblind, so my colors are a little bit off, but they are mostly to do with livestock. For example, looking into greenhouse gas focused genetic selection and breeding that Francisco has been talking about is estimated to reduce about over 500 megatons of carbon dioxide equivalent. They say at zero cost. I don't believe that. I mean, there's always a cost, but there's going to be quite huge potential there. Optimizing the animal feed mix, which I'm going to be talking about, another huge potential. Looking into the expanding the use of processing and improved digestibility. Again, I'm going to talk about that as well. We have some options there. Expanding using technologies that increase livestock productivity and efficiencies. I'll touch on that. And expanding the use of animal feed additives, which I will be talking about as well. So a lot of those issues that will help us get into net zero are to do with livestock. And so hopefully today I'll give you some highlights on what's happening, what the potential is, and where the future direction is going to be. This picture, I think, summarizes quite nicely what are the methane mitigation strategies. This is a paper that we published in PNAS last year. It's a lot of meta-analysis has been conducted for different types, but in general, you can group them into those that are to do with animal and feed management. So a number of things that are happening there. Or you could look at diet formulation using things like lipids or byproducts and manipulating basically the diet, and the rumen manipulation, looking at feed additives and potential electron sinks as well. So there are a lot of strategies that we have, and today I'm going to be mostly talking about those that are related to forages and additives as well. This is a paper that was published just a couple of months ago, and I'm not expecting you to read everything here, but basically trying to group the different strategies into those that gives you relative reductions. So the first part to deal with the feed and with forages is mostly in terms of relative reductions. That is reduction per unit amount of yield or per the dry matter intake is the reduction that you see there. The second part is using the additives, different type of additives that have been developed and are in development. And we have and then they have secondary plant compounds as well. So the last two are kind of absolute reductions of methane emissions, while the first part is relative reduction in emissions. So I'll try to go through some of those mitigation options and why they work, and what kind of things that we need to think about and make sure that we are not swapping one emission with the other. So starting with the improved animal productivity, this is a life cycle assessment that was conducted for California, and we looked at we compared what used to be in the 1960s and in 2014 in this case, to produce 1 kilogram of milk. So this is energy corrected milk. In 1960s, we had a total of about 2.1 kilograms of carbon dioxide equivalent per kilogram of milk, while in 2014 it's about 1.16 or 1.12, depending on different models, but it's quite similar, around 1.2 kilogram of CO2 equivalent per kilogram of milk. If I were to do this again now, we would actually go lower than 1. I think we are around 0.98 or so kilogram CO2 equivalent. So this is a lot of this to do with productivity. This is, as Francisco showed, the increase in milk productivity. He showed about doubling of this milk production in the last 50 years or so, and all of that then happens. It helps in reduction of emissions per unit of output. So this is actually a conservative estimate. There are some greater reductions are expected in carbon dioxide and nitrous oxide as well. So if we were to include those, we will actually see a lot more reductions as well. The other thing that's really important in low and middle income countries, where we're going to have the majority, or we have the majority of animals, is that intensification through improved feeding practices, which is both quantity and quality of feed, and animal management and improved animal health, and breeding for greater productivity and better reproductive performance. All of this will result in greater individual animal production. And then as the production of the individual animal increases, then the emission of methane based on animal product goes down as well. So this is the reason this is happening, is because of the dilution of maintenance effect. So as the nutrient intake increases, the proportion of nutrients that are ingested used for maintenance functions decreases, and it leaves a greater amount of the feed intake for animal production. So how do we do that? So in case of a lot of the low and middle income countries, there is an issue in actually putting together a ration formulation, understanding the feed, what's the feed available in the country or in the region, and how you put those together in order to improve productivity. So what we've been working on with the help of USDA, Foreign Agricultural Service, with USAID and Gates Foundation and others, is to put together a ration formulation software in the language that people use for specific breeds of cattle. So in this case, for example, is from Laos. You can choose your language with the English or in Lao language, and then you can choose your different animals, and that then help you in doing that. So there's a screenshot of another one from Ethiopia. It's all in Amharic, and so that really helps in spreading the use of ration formulation software among farmers and among extension agents as well. Realizing that a lot of people won't have access to computers, this is now being changed into a mobile app. So you can have a mobile app device, and that will load it with the feed available for that region already, and then you will be able to do this ration formulation on the spot without having to have access to internet. So that's one way of increasing the productivity and reducing emissions indirectly. I'm going to go through some of the impacts of using forages and manipulating forages and how they relate with methane emissions. So increasing forage digestibility usually increases dry matter intake and improves animal performance. That then decreases methane yield. So when I take methane yield, I'm talking about methane per kilogram of dry matter intake. When I talk about intensity, I'm talking about methane per kilogram of milk production or weight gain. So the digestibility of forages conserved as hay or silage can be maximized by harvesting at a vegetative stage. So try to avoid they become too mature and too fibrous. And in grazing systems, digestibility can be improved by optimizing grazing management to decrease the forage maturity. And although methane intensity decreases, the absolute methane production due to increased forage digestibility usually remains constant or sometimes increases as well, because it will enhance dry matter intake and it will increase the organic matter fermentation in the rumen. So there are a number of genetic manipulation to help improve the digestibility of forages, which will then reduce methane emissions. And at the same physiological stage of maturity, legume forages contain less NDF than grasses. And although fiber in legumes is more lignified, the decline in fiber digestibility with advanced maturity is actually much greater for grasses than it is for legumes. particularly in tropical situations. And some legumes can contain secondary plant compounds that will decrease methane production. So we'll talk about tannins and essential oils later on. The rate of passage from the rumen and also because of the dry matter intake can be greater for legumes than grasses. And this will theoretically reduce methane yield as well, because the reason there's going to be more methane is that because the microbes are acting on this fibrous material and producing hydrogen. But if the feed is moving more quickly, then you have so it doesn't stay that long. So you do have less amount of digestible material to be converted into methane. And animal performance is often increased with inclusion of legumes in ruminant diets, which also then decrease methane intensity. Perennial legume forages, they biologically fix nitrogen, which reduces the amount of nitrogen fertilizer used and associated emissions with that as well. So the net effect of increased use of perennial legume can be complex, and it could be very much regionally specific as well. So we do need to do a life cycle assessment before we can recommendations can be made to use perennial legumes. Another thing with forages is that if you use high starch forages such as corn silage and small grain cereals, this can increase starch and decrease fiber concentration of diets. And so the resulting rumen fermentation then promotes propionate production, which competes with methanogenesis for metabolic hydrogen and can lower rumen pH and inhibit methanogens as well. So higher propionate production is usually associated with lower methane production, because propionate takes away hydrogen and it reduces the amount of hydrogen that's available for the methanogens to use and convert into methane. With some diets, incorporating high starch forages increase digestible energy intake of animals, and therefore it enhances the animal performance, and so it decreases methane intensity as well. There were some meta-analyses that have been done using corn silage, and it showed that there was a positive correlation with milk yield, and a negative correlation with NDF concentration. So we would expect about 15% reduction when using this kind of activity. In this figure here, what the researchers have done is looking into replacing corn or replacing alfalfa with corn. So the lower bar with the solid square dot says 0% corn silage, and then it moves on to 50% corn silage, and then at the end, at the top here, with a circle, closed circle, is 100% corn silage. So you can see that the amount of propionate that's being produced increases quite substantially, and that means that there is going to be less amount of hydrogen available, and there's less amount of acetate and less amount of methane from that as well. And then there's also evidence that shows there's a better use of nitrogen. And then when you do an LCA, it showed that about 2.5%, 3% decrease in carbon dioxide equivalent per kilogram of fat and protein-corrected milk for corn silage compared to alfalfa silage in the diet of lactating dairy cows. Another way to reduce emissions also could be using forages that are high in sugar, or developing genetic lines that contain high sugar. And this is because high sugar cultivars of perennial ryegrass, for example, they have elevated amounts of water-soluble carbohydrates, and mainly at the expense of crude protein and in some cases NDF concentration as well. And then the greater concentration of this readily available carbohydrate then decreases the acetate to propionate ratio in the rumen. In vitro, it has been shown that methane production for high versus low sugar grasses, that you see less amount of methane in high sugar grasses. There was some moderate inverse correlation between the water-soluble carbohydrate concentration and various expressions of methane production as well. And in a recent meta-analysis, this was reported back in June, it showed that for every 10 gram per kilogram of dry matter increase in water-soluble carbohydrate content, they saw a methane yield decreasing by about 0.3 grams per kilogram of dry matter intake. So obviously there is a limit to how much you can do that, but there is that little bit of room to be able to come up with high sugar varieties that would then help reduce in emissions. But at the end of the day, life cycle assessments of milk production need to be done, and the one that has been done so far has shown about 3% reduction in emissions per kilogram of milk when you compare dairy cows that were fed high sugar versus conventional ryegrass pastures. Another important aspect on the forages is the preservation and processing methods. So the effect of ensiling forage on methane production is expected to be highly variable depending on the forage quality and the ensiling practices. And the impact of preservation methods on methane emissions is really mostly because of the effects it has on animal performance, which then affects the methane intensity. And processing of forage by either grinding or pelleting reduces particle size, which then increase rumen passage rate and then decreases organic matter degradation in the rumen, which then shifts the fermentation towards propionate production, with then you have less amount of methane production as well. And for forage preservation and processing increase the use of fuel for machinery and other associated emissions compared to just grazing fresh herbage. So reduced NDF digestibility due to processing can also lead to increased manure emissions of methane, depending how the manure is managed. So there needs to be an LCA to conducted to figure out whether the offsets reduction that you see in methane would be a net reduction compared to the additional emissions that you need in terms of the preservation and processing methods. So now moving on from the reductions in yield and intensity into absolute reductions. So this graph kind of summarizes the potentials of feed additives and lipids in reducing methane emissions. You can see here the biggest impact on emissions. This is a summary of the in vivo work that has been done. So only in vivo data went into this graph because there's quite a big variety in vitro. So here it shows that the seaweed is probably the highest potential at the moment. Lipids next to it, and then we have a number of others for 3-NOP, and then a lot of secondary plant compounds that have the potential to reduce methane emissions. So we'll try to go through them and see what the potentials are and what need to be done in the future as well. Dietary lipids, they work reduce the methane emissions through different mechanisms. It could be through toxicity against methanogens and protozoa, through biohydrogenation of unsaturated fatty acids that are serving as a minor sink for metabolic hydrogen. It could be shifting the rumen fermentation from acetate to propionate, resulting in lower methane production. Also, as they are largely unfermentable, and so the replacement of carbohydrates with lipids will contribute to decreased enteric methane emissions as well. And the supplementation of dietary lipids as an effective methane strategy depends on different things. It depends on the form of the lipid, the source, the amount of supplemental fat, the degree of saturation, fatty acid carbon chain length, and nutrient and fatty acid composition of the basal diet as well. And the anti-methanogenic properties of dietary lipids. So the effectiveness varies quite a bit, but in general, it's between 3.8 to 4.3, so approximately about 4% per 10 gram per kilogram of supplemental fat, depending on the source. So as I mentioned earlier, microalgae has been shown to reduce emissions quite a bit. This is the first in vivo trial that was conducted here at UC Davis, and we observed about 67% reduction in emissions using a species of seaweed called Asparagopsis armata that has less ingredients, less active ingredients compared to another species. So we saw about 6-7% here, but others have seen about 80% reduction in dairy cattle as well. But after this was done, there was a lot of questions that was asked in terms of if the microbes in the gut will be able to get used to it. That's evidence that they will be able to do that in other additives. And also the stability of the seaweed itself, how long it will be stable in storage. And also the products, will the taste of the product will be affected. And also if the milk production or health of the animals will be compromised as well. So in a subsequent work is done about for 5 months, so about 21 weeks, to try to see if there is any adaptation happening within this. And also there are impacts of the basal diet. So we looked at different basal diets in here. When there is no addition of the seaweed, you see this graph where it goes kind of, it's higher at the beginning and then it goes down towards the end with no addition of any feed additive. And that's exactly what we expect, because here what you see is the effect of feed. At the beginning is high forage diet, and then towards the end in the feedlot diet is we have higher concentrates, so more corn in this in the diet. So this is exactly as expected. And now when we add a lower dose, about 2.5% of the diet, then we see quite substantial reductions. And then as you improve again, as you increase the amounts, then we go into much more reduction in emissions as well. So we estimate between 50 to 80% reduction is what we saw in this experiment. In another experiment, similar experiment in Australia, they have seen up to 95% reduction in emissions as well. And this is, now there are a number of companies that are working on this, at least 4 that I know of, and 2 of them in the US that are trying to get this into farmers' hand and get through legislation, which is a bit tricky in the US at the moment. So we wanted to understand why this is happening. Now, the halogenetic compounds such as bromoform, they accumulate in specialized glands in seaweed as a defense mechanism. And we've actually known for a long time that halogenetic compounds do reduce methane emissions. And so we did a study with a colleague of mine, Matthias, looking into the comparative omics analysis to see if the reduction in methane was caused mainly by reduced abundance of the methanogens, are we killing off the methanogens, or is it by downregulation of methanogenic genes and pathways? And the results show that the abundance of the methanogenic population actually remains stable, and the reduction of methanogenesis in the presence of this seaweed was triggered by downregulation of several genes of the methanogenesis pathway. So this gives us a really great insight into how this is working, and so gave us an idea that then, if we are able to manipulate the microbiome and knock out some of those genes that are responsible for methanogenesis, then we may be able to come up with a solution to really reduce methane emissions. The issue is that we don't have the tools to be able to do that. So we are teaming up with folks at the Innovative Genomics Institute at UC Berkeley, who are very well known for their work in CRISPR technology. So they will be working to optimize microbiome editing technologies, and then we'll use those technologies, and we'll see if we're able to do this editing in the microbiome and test it out in vitro, and to see if this happens, if there's a resultant methanogens with knockout genes actually do produce or do not produce methane. If that is successful, then we plan to inoculate this into calves before the rumen is fully developed, so that it gives these methanogens a head start. and in the hope that they will be the first colonizers, and they will be the ones, the majority, so that the methane emission could be substantially reduced. So this is high risk, high return type of thing. We still don't know if we're going to get the funding needed, because this is quite a large amount of funding that's needed. But hopefully by this weekend we'll know if this is going to go ahead or not. Moving on to another very, very promising feed additive is the 3-NOP, and it has been shown there's been over 40 experiments conducted in vivo, and that's consistently shown that they have reduced methane emissions by at least 30%. There was also work done to look at the effect on manure, and there was no significant differences in emissions from the manure from animals that have been fed 3-NOP or 3-NOP with monensin or nothing at all. So there's no downstream effects on feeding this, and then upstream there will be some for production of the 3-NOP itself, but other than that, we see that's over 30% reduction. We actually published this month a paper on a meta-analysis to quantify the impact of this particular feed additive. And what we see is that the overall mean, this is only in dairy cattle, the overall mean is almost 33% reduction in dairy cattle, but this is modified by the dose of 3-NOP. So as you would expect, the more 3-NOP you give, the more effective it is. So the more reduction that you're going to see. And it's also modified by the fiber content of the diet, just very similar to what we saw with microalgae. When we have higher NDF, there's lower effectiveness. The same thing here also. At high forage concentration, there's less effectiveness as well. So when you're trying to estimate this, you really need to use an equation to describe what the expected reductions in emissions is going to be. One really interesting work that gives us a lot of hope to the ambitious project that I mentioned earlier is that in this long-term study, they have seen a persistent reduction in emissions by giving 3-NOP only for the first 14 weeks of life. So before the rumen is fully developed, they gave the 3-NOP, and then after that, they stopped the 3-NOP, and then they just kept measuring emissions. And as you can see from this figure, it continuously to have a reduction. So up to at least about almost a year, there is a significant reduction in emissions continuing. And I think this work is ongoing. It will be very interesting to see if those animals going into lactation and during lactation, there will be a reduction in these emissions as well. Another strategy is to use electron acceptors. So this alternative electron acceptors can be organic, like fumarate or malate, or it could be inorganic, like nitrate and sulfate. And these compounds that draw electrons away from methanogenesis and incorporate them into alternative pathways. And in general, the in vivo effects of malate and fumarate on enteric methane production, they range between no effect in some studies to some mild or moderate effects between 10 to 20%. And the average decrease in methane production in which nitrate was supplemented was estimated to be between 14 to 17%. So we did a meta-analysis a couple of years ago looking into nitrate and the effect of nitrate, and what we've seen is it was more effective in dairy than it is in beef, just mainly the way that it was given. But it's about 14 to 17% reduction in emissions. But the issue is that nitrate can be partially converted into N2O in the rumen and can be expelled. But even more important is that nitrite is an intermediate in the reduction of nitrates to ammonia that can be absorbed through the rumen wall and can react with hemoglobin to form methemoglobin, which cannot transport oxygen. So basically, it will lead to death because there is no oxygen delivered by the blood. But it is possible to gradually adapt the rumen to nitrate supplementation. Nitrate feeding currently is not approved in North America, but carbon credits can actually be obtained by feeding nitrate in Australia. Essential oils are complex mixtures of volatile lipophilic secondary metabolites that are responsible for plants' characteristic flavor and fragrance. And when extracted and concentrated or chemically synthesized in some cases, these essential oils may be able to exert antimicrobial activities against bacteria and other microbes. And rumen gram-positive bacteria particularly are affected by essential oils, and they are involved in the fermentation process. And so reducing that might also reduce methane emissions. There's a lot of work that was conducted here, different type of essential oils. The jury is still out. I mean, you see a lot of improvements, a lot of reductions in emissions, but it is quite situation specific. So this is a case that we've done 3-4 years ago, looking into a product based on garlic and citrus extract. And when added at about 15 grams per day, we were able to observe about 23% reduction after 12 weeks. So for the first 12 weeks, we have not seen a significant reduction, but after 12 weeks, there was a significant reduction. So there could be a period in which there is some adjustments in the rumen. And so if we were to continue this, we might be able to see so the effect long lasting. So there's more work that needs to be done to see how long this will last and how long it needs before we can see significant reductions using various types of essential oils. Another interesting secondary plant compound is tannins. There are a couple of studies that have shown that the use of tannins reduce substantially methane emissions. Both of them here from Australia. They looked at dried grape pomace and siled ones. So they look at red varieties and white varieties. So in all cases, they seem to see a reduction in emissions. We are just starting an experiment here at UC Davis to do this as well. So we looked at different forms of different varieties of grape pomace, and we've done some analysis in collaboration with some of our colleagues in food science. And we have selected some that have a greater proportion of tannins and polyphenols and lipids as well. So in about 6-7 months, I'll be able to tell you whether there was a successful reduction in methane emissions or not. So I'm going to stop here, sort of listing a lot of those mitigation options. There are some sources that they can look into. The FAO put together this very large group of people to work on this issue, and this document will be published in April. So we are almost finishing this process now. We got a public review. We are responding to the comments from the public review. So it will be launched towards the end of April. And before that, there's a summary of that published as a paper that was published in December of last year as well. So much more detail can be found in those publications. So to summarize then, there are different mitigation strategies. There could be relative reductions, so product-based reductions or absolute reductions. In terms of the product-based reductions, we have increasing feeding levels, so that's improved productivity, grass maturity, decreasing dietary forage to concentrate ratio. And they are sort of relevant in different systems here, the feedlot mixed systems as well as the grassland systems. And there are absolute reductions, a number of those things that we have talked about. And one thing I wanted to add is that there may be some impacts on other things as well, particularly in milk production and gain for beef cattle. These are important because if they are going to compromise milk production and gain, then they may not be effective strategy to do that. So we want to make sure that milk production is not compromised. In a lot of the absolute reduction technologies, the milk production is not really, there's no effect in most cases, or gain, there's not much effect in there. So the effect is on reduction. So the question that came up earlier in terms of what are the incentives are going to be quite important for this. So just to conclude then, the livestock industry has really done a lot of work over the last 50 years. And we have now a lot of different ways to be able to reduce emissions. looking at forages. I've listed a number of ways to work on forages and come up with reduction in emissions. Feed additives, these are just the tip of the iceberg. I think there's a lot of other feed additives that are in development right now. So we'll see a lot more of this coming up in the next few years as well. And then really interesting stuff that Francisco also shared, working in microbiome, working in genetics. I think this is really exciting time to be involved in these studies. So I just want to say thanks to all my students and postdocs who are on the front line and who do all this hard work, and also a lot of the funders that help us with a lot of this work as well. So thank you, and happy to answer questions.
Okay, thank you very much. Very, very interesting. A lot of information, obviously, but also I think a lot of opportunities, including, I think, for forage breeders. And I don't know to what extent forage breeders are already looking at some of these opportunities, but there definitely are a lot of opportunities here for to capitalize on what AG2PI really stands for, right? Is going across livestock and crops, and I think this is forages is feedstuffs is one of the areas where there's the most direct link between crop production and animal production. So thanks for that. We have a number of questions, and again, if you put them in the chat, we'll try to get to them. Otherwise, we'll ask the speakers to answer them offline. Regard to seaweed, did it have any impact on composition or milk yield? And then also, what is the cost of it, and is enough available to meet the needs?
Yeah, they're all good questions. So maybe in reverse order. The cost we don't know. They're not available for sale at the moment, so we don't know the cost. But I'm sure they'll come up with something that is that farmers can be able to use, and maybe link it with carbon credits. And in terms of changing composition, we have not seen any change in composition and of milk, and so the milk yield in our work, it was compromised because the feed intake went down when we increased the amount of seaweed about to 1%. Then there was a reduction in intake and milk yield. But since then, things have changed, and that was the first trial. Now the ones that are available are sort of the maximum is about 0.3%. So 0.3% is quite low. At that point, I wouldn't see any reduction in milk yield.
And you had some information on the what might be the active compound in seaweed. So is there an opportunity to feed that directly as an additive?
Yes. Actually, there is a company based on Australia called Ruminate that have come up with a way to stabilize the active ingredient and directly feed this to the animals. The only thing is that bromoform at the moment is a potential carcinogen and is not allowed to feed to animals. So there's going to be some regulatory challenges there. But yes, there's another company also based in California that are coming up with solutions that does not have, it's inspired by seaweed, but not really seaweed. So they can really manufacture it and produce it in large quantities and fairly easily. So I forgot to mention to answer the question earlier in terms of the scaling up and availability for seaweed. That's going to be a challenge, but I think those companies that are working on at the moment seems to think that they would be able to solve the issue in terms of scalability.
So it's a related question. What's the regulatory status of the different feed additives in the US?
In short, it's a headache. That's actually one of the biggest problems we have in the US is the regulatory framework, because it is when you reduce methane emissions, it's being considered as a drug. So anything that reduces methane emission is looked at by FDA as a drug. So it has to go through the drug approval process, which makes it very, very difficult, and which is also unique. And European Union does have a different way of looking at feed additives. They've already approved some feed additives. Australia, New Zealand, and most other countries, they don't have this issue. So it's specific to the US. And I think FDA is looking into this, and I'm hoping that they will come up with a solution to look at those feed additives in specifically. But at the moment, it's a roadblock. You know, it's a big problem to have.
Yeah. So both you and Francisco talked about the opportunity to manipulate the rumen microbiome. So there was a question stating that, well, the cow and its microbiome have evolved for millions of years. So is there a potential that if we try to manipulate it, that there will be negative side effects?
Yeah, I mean, definitely. I mean, there could be some potential negative effects. I mean, that's why we're trying to understand the mechanisms that are involved in methanogenesis, right? So what we are thinking in the project, in the potential project that I spoke about, is to not reduce the amount of methanogens per se, but just changing sort of the knock out the genes so that we have a downregulation of those genes that are responsible for methanogenesis, so that we don't have methane. So what we've seen before is, you know, the accumulation of hydrogen does not seem to have a negative effect on the animal. There's basically hydrogen is being eradicated out. We've done this in beef cattle for 5 months, and there's no problem at all. And you see an elevated amount of hydrogen, but other than that, they can maintain very low amounts of methane emissions for a long period of time. So yeah, I mean, there could be potential pitfalls that we don't know, but I mean, that's why we have to do this work.
Yeah. Any thoughts on that, Francisco?
Yeah, no, I agree with Ermias. Probably there will be some potential negative effects. I like to think that there will be some limit, right? So we are here, and there will be some limit where we can actually manipulate the rumen until that limit without running into troubles, and that will allow us to reduce methane emissions without, of course, getting zero methane, but reducing through manipulation. Again, I think there is room to manipulate without observing negative effects, and of course there will be a limit. There is another question I think is interesting, Jack. Ermias was talking about diet and what's the interaction between nutritional intervention and selective breeding, and I would say they are the best friends, right? You can actually have a national evaluation for methane emissions, and at the same time you can have nutritional interventions to mitigate methane emissions. Something that is interesting and we don't know is what we discussed, Jack, before. What if now I have genotype by diet interaction, and then we will need to be careful. But of course they are not antagonistic at all, and that's the idea of combining multiple approaches. Mm-hmm. Yeah. I don't know, Ermias, what you think.
Yeah, absolutely, I agree. I think we have to do multiple approaches. I think just there's no silver bullet, so we have to use multiple approaches to be able to substantially reduce emissions.
So when it comes to the different approaches, the question, which of those can be most easily adopted in poor and developing countries?
I think for me, the improving productivity is the way to go, and that's why we've put a lot of efforts into that and developing those diet formulations, and investing on feed, and understanding what feeds are available, and improving the availability of feed. That's really the best way, improving productivity, and then really getting reductions in emissions per unit of milk. Because otherwise, what's going to happen is that you just increase the number of animals. So really, the one thing that we can do is, obviously improve the genetic merit of the animals. But then, if there is no nutrition to back it up, then it's not going to work. So that's what we're focusing on at the moment.
Yeah, I think that's a very important message, that improving productivity is the most effective strategy to reduce environmental impacts of livestock in general, right? And yeah, we've been doing that for decades. But there is obviously opportunity to go beyond that, to directly measure emissions and change the diet. So Fortunately, we're going to have to close it off here. This has been a very interesting session. Very much appreciate Francisco and Ermias, their presentations and the discussion, and all of you for putting in your questions, which again we'll try to get the speakers to address offline. We have we're going to be back on our regular schedule next week or next month in terms of being on the third Wednesday of each month. And there are also going to be some new workshops that will be announced fairly soon. Keep an eye on the AG2PI.org website. And then in the summer, in June 15 and 16, we'll have a conference. We'll send more details out later, a conference at Kansas City on mapping the future of AG2PI or AG2P research. And so we need everybody's input from all different sectors, including industry, into that, because it's going to be the basis of information that we provide to NIFA in terms of what research should be funded or what the priorities should be for future research in this area. So with that, I want to thank everybody again, also Nicole for all her work in getting this organized, and hope to see all of you next month.